very much. So my final lecture is about the expansion in groups and explicit expanders, which are a related concept, because when we say explicit, the nicest thing we can hope for is to present our expander or our Ramanujan graph or Ramanujan complex as a Cayley graph of a group that we know. And when we talk about expansion of group, we want to do the other way around. Start as a group and find nice generators that give a good expander graph. So here I am. Let's get back to the LBS construction. You remember we got there Cayley Ramanujan graphs on phi either GL or SL of the finite field with Q element. So there are some hints how this happens in Alan's talk and in Francois' talk, and I want to get deeper into this and to understand what we need to do to take it to higher dimension. So the idea is we're trying to not work on this graph directly, but to work on the universal cover, which is the tree or the building, and put on that the Cayley structure. So let's say B is the building of P, G, L, D, Q, P. Now you remember that vertices correspond to G mod K cosets, where this is G and K is the maximal compact subgroup. And some people, when they begin with that, they make the mistake of thinking that the building itself, or at least its one skeleton, should be the Cayley graph of G or the Schreier graph of G mod K. So, what is the Schreier graph of a coset space of a group? You take some generating set. The Schreier graph is the graph whose vertices are cosets, and the edges are G. Each coset is connected to the coset GS. GH for every G in G and S in S. But what happens in the building? So I'm looking at the one skeleton of the building. So this is if I put here B1, it's only the edges. One parenthesis is vertices and edges as a graph. And the building, I think it was said, the building is the clique complex of the skeleton. So once you know the skeleton, you can just fill in the missing cell. This really has vertices G mod K, but the edges are not this, but actually GH is connected to GSH for certain S. Very specific ones. We just take ones and then P's. You can take how many P's by ones you want and how many P's. Not everything 1 and not everything P. And connect each coset to all of these cosets, and this will give you the skeleton of. This is the simplest way to define the affine building of PGLD. But it's quite confusing, because here, for example, you see that every coset is connected to S different cosets.
This is this in the fundamental apartment, no?
No, this is the entire building. What happened? Here there are D minus 1 operator, right? I can put 1P, 2P, 3P, up to D minus 1Ps. So you could think I'm only telling you, so this has degree D minus 1, but the point is, you can also write G, sorry, this is K. We're talking about cosets of k, which is a very specific k. The point is you can write every gk also as g little kk for any k in k. Right? The same coset has many representative, but now we need to connect this representative to g little k as k, and there is no reason that this will be the same as g as k. So this is why you actually get your many edges, and this is quite misleading, but it's a good way to think about it. Now the point is, so this is not a Schreier graph. I've been calling this a Hecke graph, then somebody told me that some people call this Cayley Abel graph. Yeah, so I heard that name before. So this is a Cayley Abel. Abels? Okay. Ah, so yes. So I'm told it's not the Abel that I think of. Okay. So it's a Cayley Abel graph, but the point is we want to make it a Cayley graph because we don't know how to play with this thing nicely. And the idea is the following. So recall, we took I took G. I think let's stay with Francois talk. Or we took G was the group of Hamilton quaternion, invertible Hamilton quaternion modulo the center. And then we took gamma to be the S arithmetic group, which set as a lattice is in a co-compact lattice in GQP. And yes, first it sits as a lattice inside GR cross GQP, but then we recall that GR is compact, so we throw it away. And the point is that this is isomorphic to PGL2QP for P, let's say, congruent to 1 mod 4. That's an easy exercise. 3 mod 4 is a bit harder exercise, and 2 is false. But let's stay with 1 mod 4. So this is how we got a co-compact lattice here. And we're going to take some finite index subgroup. And the following are equal. So one of them is gamma is a transversal for G mod K. This means that if you consider the map gamma cross K to G, and you send the pair to its product, it's 1 to 1. So you get a splitting of G into K and lambda, except that this is not a direct product or semi-direct product because neither is normal in G. But it's still very useful. The second is that lambda acts on the building simply transitively. And the third is that taking S to be the element, let's say, all the element in lambda, all the element in gamma, we take your fundamental vertex in the building to a neighbor, you get that the Cayley graph of lambda with respect to this S is exactly the one skeleton of the building. So this is all tautology. It's nothing deep here. This is the orbit stabilizing theorem, and we already established that that S are the group of neighbors, and that the vertices correspond to the elements of lambda. And now by the translation action of the group on its Cayley graph, every element, the neighbors of every element are its translation by S. So you can think about it like this. Now instead of connecting GK to GSK, which is very annoying. We replaced every coset with a unique element coming from the transversal, gamma in this lattice. And yes, we connect it to gamma S, but there's no coset here. So it's a right Cayley graph, but it's a Cayley graph. There's no coset to annoy us. Once you have a Cayley graph, you know how to take quotients. So for example, we can take lambda q, which is the kernel from lambda to the group over fq. You remember that lambda sits in gamma, which is just the group over z1 over p, and this maps here if p is different from q. So look what happens here, and we get that if I want to look at for the complex, which is the building divided by lambda q, I get that the one skeleton of this complex. So now I say again, okay, I can forget about the cells. Everything comes from vertices and edges. This this is the quotient of the Cayley graph now of lambda with respect to the generating set S. But the quotient of a Cayley graph by a normal subgroup, and everything would work with a non-normal, then we'll get a Schreier graph. But if it's normal, I even get the Cayley graph of lambda mod lambda q with the projected generating set. And now, okay, so we can stop here and say, okay, this is already a finite group, so we're happy because this was finite index here. Index is bounded by the size of this finite group. But actually, this is going to sit somewhere between G FQ and G prime FQ, and this is by strong approximation. As Francois told us, strong approximation doesn't hold in general, it holds for a simply connected group, the one with no characters or co-characters or both, I don't remember. But once we go to that group, we know we're at least on the image of this group here. And this is, of course, because we mapped here. So this is just the kernel image theorem, 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 image theorem,